basis for my presentation because he explained the basics of semiconductors. In my talk, I would like, first of all, to discuss what kind of task is device modeling, and to justify the necessity of many simplification for real simulations. And then I will discuss the major equation used for device modeling and use the p-in junction, simple p-in junction as an example. This will repeat some ideas presented by Claude, but nevertheless there are some nuances that it's worth to discuss. And of course I will speak about the LEDs and discuss what we need for efficient light emission. And I will discuss how is the state-of-the-art LED structure designed, and explain the difference between the simulation of the LED structure and LED dies. Because not only the structure is important, also the processes occurring in the LED dies are also of issue. And we will discuss all the necessary elements of device simulations. First of all, practically all the devices are electric devices, and that is why the determination of electric potential is the primary task. If we know the distribution of electric potential in any LED structure, any device structure, we can predict the current flow in the devices. And the current flow changes the density of movable carriers. That is why there is very strong coupling between the electric potential simulations and current flow. If we have electricity, in this case, there is some ohmic and non-ohmic losses. And these losses results in the generation of heat inside the device structure. The heat generation produces non-uniform temperature distribution, and temperature distribution has a weak coupling with the current flow issues because practically all the parameters are temperature dependent. I mean the material properties. But if there is non-uniform temperature distribution in any devices, this produces the thermoelastic strain. And this strain, especially if we speak about the piezoelectric materials like gallium nitride and so on, this strain affects considerably the electric potential. There is also the reverse piezo effects, producing weak coupling of the electric potential, weak influence of electric potential on the strain in the LED structure. And if we speak about the LEDs and other optical devices, we should consider the light emission. And light emission is dependent on the current flow, on the heat transfer, and so on. Unfortunately, in most cases, all these problems should be solved self-consistently. And this solution is used in order to predict a limited number of device characteristics. As a result, we can, and also we should speak about the quantum mechanics, because quantum mechanics is involved in light emission, in the current flow, electric potential, and even in the heat transfer. So actually, the device simulation is essentially a multidisciplinary task. What about the spatial scales? I would like also to show you the different spatial scales using LEDs as an example. For instance, if we consider the active region of the LED quantum well, typical width of the quantum well is 2-3 nanometers in the indium gallium nitride materials. If you consider the LED structure, the thickness of LED structure is a few micrometers. That is a typical. If we consider the LED die, in this case, in the case of high power LEDs, typical dimensions are 1 by 1 millimeter. And finally, if we consider LED lamp, where the light conversion can be also used. In this case, the typical dimension are a few centimeters. So in total, there is 7 orders of magnitude difference in the spatial scales. What does it mean from the point of view of modeling? We cannot use the unified grid for numerical simulation. We should use every particular grid for every particular time scale. And we should arrange a coupling between the simulation of different processes occurring in the state-of-the-art devices. One more issue. So this means that actually we have a multi-scale task. And what is especially important, you can see here the realistic configuration of the ohmic electrode and realistic configurations of electrodes in the other case. So you see that is a very three-dimensional configuration. So actually we have multidisciplinary task, multi-scale task, and also we should carry out simulation in three-dimensional approximation. This requires much time, and this task is very computer resource consuming. On the other hand, the people who want to use simulation in practice are interested, first of all, in very short time necessary for getting the the guidance helpful for their everyday activity. That is why we cannot do the full throughout simulations. We should think about simplification of the whole task. And what kind of simplification are used in practice? First of all the quantum mechanics is avoided. I'm sorry, this doesn't correspond to the topic of our workshop, but that is a real life. Then, instead of solution of the elastic problem, people take into account only the mismatch strain in the structures. And mismatch strain is considered analytically using approximation of the uniform strain in every epitaxial layer. The next simplification relates to avoiding the thermal issues. Because in many cases, when the device is small, in this case, we can substitute the whole problem with some effective temperature of the active region of the devices. And this simplification is very useful for practice. And finally, the optical phenomena, if it is possible, are substituted by a simple models of carrier recombination. So as a result, we have some minimal model, which includes the consideration of electric potential and current flow. And this model is very popular among the people because approximately 80% of all simulations of the devices is used just using this simplified model. Well, now let me make a short introduction in the operation of p-in junction. To some extent, this will be a repetition of what Claude has presented in his talk, but maybe some illustration by simulation will be helpful here. If we have the N and P-type doped materials and make a contact of these materials, in this case, electrons from the N-type semiconductors go to the P side and start to recombine with the hole in the P side. The holes go to the N side of semiconductors, and as a result, a space charge region are formed on both sides of the p-in junction, and space charge region is made of the ionized donors and acceptors on both sides of the p-in junction. This space charge region produces the electric field, and electric field produces a high barrier preventing the electron penetration to the p side of the p junction. And such a barrier is also valid for holes who try to penetrate into n side of the devices. In this band diagram, the shaded region indicates the forbidden gap or band gap. And this line represents the distribution of the electric field inside the p junction. Because there is asymmetric doping, the n-type doping, the doping level is an order of magnitude lower than in the p side. In this case, the distribution of the electric field is also asymmetric and non-uniform. And before we consider what happens if the bias is applied to the p junction, let's discuss the different channels of carrier recombination in the semiconductors. The first important channel is the Shockley-Ritz-Holt non-radiative recombination. In this case, this recombination is mediated by the deep levels in the band gap of semiconductors produced by defects. And therefore, the rate of recombination is proportional to the concentration of defect producing these levels. Then electron can be captured by this defect level, and then they can transfer to the valence band, which is just the same as the hole is captured by this defect layer, and hole then annihilates with the electron captured before. So this is one important channel of recombination. Another channel, also discussed by Claude, is radiative recombination. In this case, the electron directly is transferred to the valence band, producing light. Because this transition involves the energy transfer, and energy is transferred to the photons, and photons are emitted. That is a very helpful process for light-emitting devices. I forget to say that in the case of Shockley-Ritz-Holt recombination, all the energy differences, this energy is transferred to phonons. So actually, this kind of recombination produces only heat, and it is not helpful for light emission. And the next important process is Auger recombination. In this case, electron is transferred to the, recombines with the holes in the valence band, but the excess energy is transferred to the third particle. In this particular case, it is transferred to another electron. Electron increases his energy, and then his energy is released by cascade emission of phonons. So again, we get heat as a result, and this is also the non-radiative recombination channel. The third particle may be not only the electron, it may be the hole. So actually, there are two Auger processes. One involves two electrons and the hole, and another involves two holes and electron. How can we describe the rate of the recombination? This is a simplified equations, and this is the Shockley-Ritz-Holt recombination rate. It is proportional to the concentration of point defects, to the concentration of electrons and holes, and also as a parameters there are Ni, which is the intrinsic carrier concentration, and it is dependent on temperature, on the energy gap, and on the effective densities of states in the conduction and valence band. And also as the parameters are the cross-section of the capture of electrons and holes to the defect level, and thermal velocity of the carriers. The radiative recombination can be described by these equations, and here B is the radiative recombination coefficient. And finally, the Auger recombination includes two processes. I talked about, one involving 2 electrons and a hole, and 2 holes and electron, and Cn and Cp are the Auger recombination coefficients, the respective. In practice, people try to simplify this simple equation further. So in the wideband semiconductors like gallium nitride, we can introduce the effective carrier concentration, and also some asymmetry parameters, which is the square root from the ratio of electron and hole concentration. In practice, the asymmetry parameter is a function of concentration, but it is weakly dependent on the concentration. In this case, we can obtain the simplified equations where the Shockley hole radiative recombination is proportional to the effective concentration. Radiative recombination is proportional to the square of effective concentration, and also the Auger recombination rate is proportional to the third power of the effective concentrations. And since there are 3 coefficients, A, B, and C, so this model is in practice called the ABC model. It is very popular for interpretation of the experimental data. Well, what happens if we form electrodes on the P and N side of the pin junction and apply the forward bias? The forward bias produces external field which is directed opposite to internal field in the pin junction. And if this field is strong enough, in this case, the barrier separating the PEN region practically disappears. This means that electrons from N side can go to the P side of semiconductors, and also holes go in opposite direction, and we have electric current. So the forward bias produces the electric current in the PN junction. This is just for memory what was in equilibrium where the bias was not applied. What is also important, electrons come to the P side of the pin junction, and the concentration of electrons drops down because of recombination of electrons with the holes which are in a great amount in the P side of semiconductors. The same situation for holes. In this case, electrons and holes can be characterized by the I'm sorry?
Just a small question.
Yeah?
For the sake of completeness. You just said that on the equilibrium, the PN junction doesn't emit light.
I didn't say that. I said that in equilibrium there is no current.
There's no current.
No
but
current.
Is there light?
Huh?
Is there light?
Generally, yes. But in this case, I would say that there are 2 processes. You just talked about it. One process is absorption, and another process is generation of light. And they compensate each other. So as a result, we have no luminescence. Something like that.
I would say that you have some thermally excited electrons holes in the depletion region, and so you have light, and the energy is supplied by the lattice.
Well, I would say the situation, it depends if we consider the bulk semiconductors, where the compensation of absorption and light emission take place, or limited devices. In this case, you can see the luminescence, but in this case, the driving force for luminescence is the thermal generation of carriers. So actually, we can get the light from the heat in this particular case.
Yes.
Okay. Well, now I would like to explain the basic equations used for modeling. Starting from one of the Maxwell equations and expressing the electric field, the gradient of the electric potential, we can obtain the Poisson equations, which determines the distribution of electric potential in any devices. In this case, the Poisson equations has a right side, the source, which includes different contribution to the charge density. This is a contribution for from the ionized acceptors and donors, and also from the electrons and holes, which are the movable carriers in the structures. There is some relationship between the carrier concentration and electron and hole Fermi levels. Yeah?
Where do you get the electric constants from?
What?
The electric constant, the epsilon?
Epsilon.
How do you usually
This is the electric constant. It is fundamental constant. And here is epsilon is the static dielectric constant. Yeah.
Do you get it from experiments, or do you get it from?
It is usually taken from experiments. So this is a material constant which is known for most of semiconductors. And in the case of conventional 3/5s, I'm sorry, the static dielectric constant is the real scalar value. Well, so it is important that all the contributions to the charge density depends on the position of the electron and hole Fermi levels. So if we know their position, we can solve the Poisson equation and obtain a distribution of electric potential. How can...
Another question about dielectric
Yeah?
constant. Do you ever worry about additional screening by the free carriers?
Yes, of course, because generally we calculate the carrier concentration, and the carrier concentration in the quantum well, for instance, they contribute to the charge density, and we take into account the screening. Do you mean?
Well, I meant take it into account in the dielectric constant.
It's possible. It's possible because it depends on the model of the electric constant. If we consider the contribution of the lattice, crystal lattice, in this case, that is just the constant I told about. If we want to take into account the contribution of free carriers, we can add a special term in the dielectric constant. And it's also possible to take into account the impact on the dielectric constant. So,
can I rephrase? What I understand from your question is that you say that you are talking about the interband fraction of the dielectric constant due to interband transitions. And of course, this changes with carrier injection. Is that the one you think of?
as far
I'm just
no.
thinking if you have a high concentration of electrons in the conduction band, there is an additional screening term which should be included in the dielectric constant. It's probably not going to...
That's what I'm saying.
Okay, we use different
So
words.
but it's a very small factor.
I assume that for carrier densities in LEDs, it's a small effect. In lasers, I think it could be important.
As far as I understand, Chris means the plasmonic effects on the dielectric constant. And they... And they, of course, can be taken into account.
Chris, are you talking about the static dielectric constant?
No, the optical. Wait, and this has both, right?
No,
Yeah.
this is static.
Well, but that has the electronic effects in it as well,
Yes.
is what I mean.
That is electronic contribution to the dielectric constant. Yeah, it is, and it is also maybe taken into account. In most cases, the contribution, for instance, for LEDs, we're operating at the practical current density. In this case, the contribution of free carriers is small compared to the to this one.
I would be more concerned about what is the value of the dielectric constant in the alloys? We take a linear interpolation.
Okay. In order to go further, we should to find the position of the Fermi levels. And for this, we should use the transport equation. This is the typical equation speculating the conservation of the electron and holes. And the drift diffusion equation, which were discussed by Claude. This is a form already presented by Claude, with the difference that here Jn and Jp are the electron fluxes, but not the current densities. And there is another formulation of the fluxes, thermodynamic formulations, which involves the gradient of the quasi-Fermi levels. In any case, these equations, together with the Poisson equations, form the simple drift diffusion model, which is used in many, many simulations. As far as we taught about the different channels of recombination, we also should mention the surface recombination. The surface represents for the semiconductors the object with a large number of defects. And therefore, every free surface capable of capturing electrons and holes, producing the surface recombination. Surface recombination is normally accounted for in simulation via boundary conditions. Well, let's consider the p-n junction again, because in the p-n junction there are many channels of recombination, and among them there is a radiative recombination. So the p-n junction may produce light. But we see from the direct simulation that the rate of non-radiative recombination exceeds considerably the rate of radiative recombination. What are the reasons? One of the reasons is that you see here from this simulation that recombination point out that electrons and holes are distributed over the whole structure. This means that there is a part of electrons that pass from the whole structure without recombination. They are coming to the ohmic electrode and are lost for recombination at all. This is the process is called as leakage. And also, the radiative recombination is non-efficient because the concentration of electrons and holes in p-n junction is very, very low. And in order to obtain the efficient light emitter, we need to introduce, we need to increase the concentration of the carriers that may produce light. Well, so the p-n junction, the simple p-n junction by itself is not efficient light emitter. Let's now consider what happens if we contact two different materials, P and N type, with different energy gaps. In this, I'm sorry?
The previous slide is it was misleading. Okay, show it again.
Okay.
You seem to imply that there's a lot of non-radiative recombination in the p-n junction. Actually, this current is very small compared to the total current which goes through.
You mean the total current includes, first of all, the leakage, which is related to the carriers that are not recombined in the structure. And this occurs only if the structure is thin enough. If the structure is thin, the leakage is small, but nevertheless, the radiative recombination rate will be low.
I completely agree with this ratio, but in a real p-n junction,
yeah,
of course, most of the current goes through.
Yes, but it depends on the thickness of the structure. If the thickness exceeds the diffusion length, in this case, there is no leakage. in thick pin junction, you cannot see a leakage. All the carriers can be recombined. Okay. Well, what happens if we?
Your examples for the NPN junction, right?
Yeah.
The previous examples. So you're assuming that the radiative recombination rate is very low in the p-type material. It's mostly electrons overshooting into the p-type.
Yes, right.
So you're assuming very high non-radiative recombination.
Right, right.
I think that's your assumption.
Okay. This is a typical p-n junction made of gallium nitride. So the thickness is approximately 1.5 micrometers only. The recombination of carriers is very low, and that is why the diffusion length is high. So actually, in this case, the leakage is very, very pronounced in this particular case.
How do you define leakage?
I define leakage as a part of current, part of current produced by carriers that don't recombine in the structure at all. That is leakage.
In their band.
Yeah, yeah, and the same for holes.
But this is specific. I mean, this is very specific to nitride diodes and recombination parameters.
I think it is specific for thin devices because if you remember the Shockley paper on pin junction, in this case, the dimensions of the pin junction was hundreds of micrometers. In this case, recombination was strong enough in order to recombine all the carriers. There was no particle coming to the ohmic electrode, and there was no leakage from this point of view. But if we consider the realistic devices, which have the thickness of a few micrometers, in this case, leakage may be very pronounced.
But I think in some of the old in-gap or on-gap diodes, they were like LPE grown. You can actually get thick diodes with high-quality material and actually get efficient recombination from minority carriers.
Okay. The typical diffusion length of the aluminum gallium arsenide lasers is from 2 to 5 micrometers. So if the structure is the thickness less than diffusion length, or maybe 2 diffusion lengths, in this case, leakage will be pronounced too. If the structure, for instance, pin junction, has the thickness of 100 micrometers, in this case, we don't see the leakage current because all the carriers have enough time to recombine on the path to the electrodes. So it depends on the competition of recombination. And also, let's consider the contact of the wideband semiconductor and narrowband semiconductor devices. In this case, if we apply the forward bias, for instance, here is the example of the contact of aluminum gallium arsenide N-type materials with the indium gallium arsenide P-type materials. What we can see, very important is the band offset at the contact of semiconductors, conduction band offset and valence band offset. Similar to the case of pin junction, we see the formation of the space charge region on both sides of the heterojunction, and this produces very specific band alignment in this heterojunction. Very specific because you can see here a local quantum well, and electrons can be captured in this local quantum well and form two-dimensional electron gas. This two-dimensional electron gas has very high mobility, and this kind of heterostructures are used for high electron mobility transistors used for radio frequency applications. Well, and now what happens if we insert a narrow band semiconductors, maybe very thin, like quantum well, between the two PAN-type wideband semiconductors. In this case, application of the forward bias produces very high concentration of electrons and holes in the quantum wells, in the active region of such devices. I would like to pay your attention that concentration is at least an order of magnitude higher than the concentration of carriers in the doped layers, which are called emitters, because from there the electron and hole are coming to the quantum well. And this effect is known as superinjection. And this is a just effect which make possible to develop highly efficiency LEDs and laser diodes. So, in contrast to the simple p-n junction, the p-n junction with inserted quantum well inside the structure produces very efficient light, because if we calculate the radiative recombination here, it will be dominant and it will exceed the non-radiative recombination. So actually, you can see here the light-emitting, the simple light-emitting diode structure. And this structure is already suitable for the practical applications.
So that's what they call a heterojunction?
Oh?
Is that what's called the heterojunction?
Actually, this kind of structure is called double heterostructure, because there are two heterojunctions between active region and N material, active region and P material.
So already the one on the previous page was called the heterojunction?
Yes, yes. Double heterostructure. In particular case, when this layer is very thin, this is called as single quantum well. Well, what kind of other active region can be used in the LEDs? Of course, thick active region with a narrow band gap. But this kind of design of active region is very inefficient, because at the same current density, the wider is the quantum well, the lower the carrier concentration is accumulated in the well. So the quantum well has very pronounced advantages. And another type of devices includes the multiple quantum well. The multiple quantum well is just a very reliable design of LED structure, because if you grow the single quantum well, any defects generated in the single quantum well destroy the device completely. In the case of multiple quantum well, there is some reserve, and if one quantum well is destroyed, other can emit light. So the multiple quantum well is really the design actually used in practice. And now I would like to show you the simulation of the realistic structure of aluminum, gallium, indium phosphide red LEDs. These LEDs emit light at 624 nanometers. And this LED includes the active region made of 25 quantum wells. And also we see here in the core of the LED structure two additional layers. This layer, you can see here, produces some barrier for electrons that can leave the quantum, the active region, and go to the P side of the structure. And this layer is called electron blocking layer. It is used when we want to confine the electron in the active region. The same for holes. Here is this layer is called hole blocking layer, and its operation is aimed at suppression of hole leakage into the N type of the LED structure. Well, what is also interesting in this picture, despite of recombination, due to a relatively low band offset in the conduction and valence band, you see a rather uniform distribution of electrons and holes among different quantum wells. It is very important because actually all the wells is well working as a light emitter. And here you can see the simulation of the radiative recombination, which is also uniformly distributed among the wells, and non-radiative recombination. The radiative recombination dominates, and this produces high internal quantum efficiency of such an LED. Well, 10 minutes, okay. When we speak about the simulation of the LEDs, we should not take into account the LED structure, but also the LED dyes. The problem is that particular geometry of the contacts of the LEDs affect the LED characteristics. And if we consider the realistic three-dimensional geometry, we need very time-consuming simulation, and we should simplify further the general task. How can we simplify this? In every particular LED structure, you can select the core, including the active region with the quantum well, and neutral region. This neutral region, the concentration of the free carriers is compensated by the charge of the ionized impurities. So in this case, we can solve not the Poisson equation, but solve the equation for the current spreading, considering every layer as a metal layer. So that is much more simpler for simulation equations. And we can also simulate the processes occurring in the active region in one-dimensional approximation and use three-dimensional model for the neutral regions. In order to match the solution here and here, we can use the results of one-dimensional simulations and use them as the boundary conditions for the matching different solutions. And finally, all this can work self-consistently. And as a result, we obtain the non-uniform distribution of the current and carrier concentration and recombination rate over the active region. From this three-dimensional simulation, we can get the IV characteristic, electrical characteristic of the devices. And using the ray tracing analysis, we can predict the light extraction efficiency and efficiency of the device as a whole. So the question is, how accurate are these approximations? So you can see here the comparison of this hybrid approach with the direct two-dimensional simulation of such an LED. And you can see here that they correlate with each other very good. A very important process is here the current crowding, localization of current under the electrodes. And the nature of this current crowding is related to nonlinear resistance of the p-n junction. Because Claude has shown that the IV characteristic of p-n junction under forward bias is exponential. So this means that the resistance of the p-n junction very strongly depends on the applied bias. And that is why changes in the local current flow in the active region results in different distribution of electric potential, and increasing of current opens the p-n junction, and this results in very non-uniform distribution of current across the LED dyes.
When you compare the hybrid and the 2D simulation, are you comparing here, is it like an average thickness or just a particular size?
Here, this line is the direct two-dimensional modeling using the Drake diffusion model.
But the other one is 1D, right?
And this is a hybrid approach.
But are you putting the 1D?
Yes, 1D plus 3D,
Right.
but
So
simplified.
when you compare, are you comparing a slice?
Uh,
Or is it an average?
Yes, this is a two-dimensional distribution, and here is the active region, black line. So we compare the distribution of the current in the active region because that is the most important slice.
These are finite differences?
Finite volumes.
Finite volumes.
Yeah.
Okay. So in principle, you would have an adaptive mesh.
Yes, it's better if you use the non-structured grids for simulations.
So have they been used here, or because with non-structured, with non-equal grids, then you probably don't even need hybrid approach.
You mean why non-structured grid?
No, so I mean, if you have an adaptive grid with different grid size, then you can use a very fine grid for your middle part and very coarse grid for your.
Let me show the grid a little bit later. Okay.
What are we seeing? Is the integrated vertical current, or is it a slice?
Here it is.
Yes,
This,
it is integrated vertical current.
this is a local current density over the active region in this direction. Yes. So P electrode is here.
Okay. It's on the top.
Yes, yes.
Okay.
From left to. Well, I would like to show how it works. We compared two different LED dyes. One is the conventional square-shaped LED, and another is a multi-pixel LED array, just suggested here in the UCSB. So this is a maybe answer to your questions. This is a grid used for simulations, and what is important? And here is the distribution of the electric current. You can see here that this and this in this point, very different current density local. And in order to resolve the distribution of the current density, we use the combination of the structured and unstructured grid. And in the case of the multi-pixel LED array, here is the temperature distribution, we need to resolve very small features in the simulations. So again, you can see here, structured, non-structured grid, and this is a more or less optimal for computations.
So this is a two-dimensional?
This is just in the plane, but in reality, this is a three-dimensional grid because we have also the structured grids in the vertical dimension. So this is just in plane. And also, we have as a grid in the vertical dimension.
Okay, but triangulation in 3D is way more complicated than in 2D.
Yes, that's right. But the main idea is that using of simplified equations based on the ohmic law accelerates the computations many times. So actually, we can solve in this grid the coupled electrical, thermal problem and predict the extraction of light. I'm sorry, I have 1 minute. I would like to show you this slide and what we can see here. Both are the experimental data obtained and UCSB. And the lines are the results of our simulations. The main idea is that in the case of square-shaped LED, the strong current crowding produces a rollover of the emission efficiency. This is just due to overheating, local overheating of the material and lowering the emission efficiency. So if the currents are not so high, the response is good. But if we go to higher currents, producing stronger temperature in the active region, in this case, we see the discrepancy. A discrepancy is related to poor knowledge of the temperature dependence of the recombination coefficient. Maybe in the second part of my talk, I will discuss this issue in more detail.
What is this 6%? What's eta back?
Here?
No, the efficient, you say eta sub back. What is this?
This is yes, right. We didn't know the exact light extraction efficiency for these devices. So we fitted the light extraction efficiency from the backside of the sapphire substrate. So this efficiency was obtained by fitting in some points. It is used for both type of devices. Yeah.
So you use hybrid model that the carrier diffusion in the quantum will later like that. In these calculations, this is the old calculations, we didn't take into account the lateral carrier diffusion in the active region. At the moment, we take into account the lateral diffusion, we take into account the surface recombination, and this is used for analysis of micro LEDs. Well,
are we in the question session?
Yeah.
Let's thank our. Okay.
Yes, it's okay. I have finished.
You have another chance later, right?
Yeah. Okay.
So we're open for questions, and your question stands between us and lunch, so bear that in mind.
I have a question. Are there any thermoelectric effects here?
Thermoelectric?
You have different temperatures, right?
Yes.
Gradient.
Yeah.
So are there fields generated by that? Are they important in this case?
They are not important. We estimated the thermoelectric contribution to the currents, and they were approximately a few % of the total current. So actually, this is just typical drift diffusion contributions.
Okay, let me continue on your thermoelectric question. Sorry, I'm continuing. You can have thermoelectric pumping in LEDs. Because if you bias at a voltage which is smaller than the emitted photon energy, you are supplying for each electron hole pair an energy smaller than the photon which goes out.
Yeah.
And still you have emitted photons because you have thermal energy coming from the lattice, which brings up the electron and hole, and so you are cooling the lattice. This is a huge area of research, because you will get cooling by just emitting light out. So it's a good question. It can happen. But this is at low current.
Richard?
The design rule for the number of quantum wells is, I think you say it was to avoid defective quantum wells, to make sure there are enough that you can find them. But I think that for the example you gave of the gas system, the quantum wells are not that deep, so you need many to overall get enough electron hole capture. Is it something that is...
Speaking about the destroyed quantum well, I meant the indium gallium nitride system, first of all. Because in this case, there are many dislocations. There are also very specific defects, like V defects, and so on. So actually, when you grow the indium gallium nitride quantum well, it's better to use the multi-quantum well structure. In general, if the growth issue are overcome, in this case, the single quantum well is as effective as the multiple quantum well.
Presumably it would have a lower drive voltage, but every quantum well presumably produces some sort of barrier.
Again, in conventional material system, the barriers are not very clear.
In aspects, you want to limit the number of quantum wells for various reasons, because there is a voltage penalty